Okay, good morning, Professor David J. Delosreyes. Okay, my topic for this session will be a long video format lecture on college algebra, and the topic will be applications of exponential and logarithmic equations. Okay, let's proceed. The subject matter for this morning will be, it's August 31, 2023. College Algebra, lesson number 47. This is now lesson number 47. We are running smooth. So for those of you who are following my channel on College Algebra, this will now be lesson 47. And the title of the topic for lesson number 47 is applications of exponential and logarithmic equations. In real life, there are so many applications of exponential and logarithmic equations. Real life problems. Okay. Okay, I will try to discuss one topic, and this will now be on the so-called radioactivity. Radioactivity. There is the so-called half-life for radioactive substance, like uranium. Okay. Uranium, the half-life is many years. Actually, we might already be out of this world, but the half-life of radioactive substances will still exist. Okay, that's why it's very dangerous for the so-called radioactive substance. The equation on how to take the half-life or the amount of a radioactive substance. Okay, this is in real life. It is given by the equation y equal to x e raised to kt. So this equation are actually general equations. And this is y, this is x, this is e raised to kt. This equation gives us the relation of the so-called present amount versus the future amount of a radioactive substance in terms of time. The value k will be the natural logarithm, okay, of the ratio 1/2 all over the half-life in years. So meaning to say, if you try to compute for the first equation, we need the value k, and to compute for the value k, this will be the equation. Okay, these equations were not derived from algebra. Actually, these equations emanate from the study of differential equations. Okay, but since our topic is just algebra, okay, I could discuss this one because I could teach differential equation, but for tonight, I will just give you the given general equations on how to compute for the equation y equal to x e raised to kt. The graph of this will be something like at time t equal to 0, it should be something like this. That's the graph. At a certain time, there is an amount for the radioactive material. But as time passes by, okay, it will decay. It will decay. But the amount is decay is actually very slow. That's why if we got the radioactive contamination, okay, it's very dangerous. Because for the radioactive substance to disintegrate, it will take us so many long times, okay? A very long time. Okay, so the graph of this is actually, it's like this. The horizontal axis is actually, no, the horizontal line is actually a horizontal asymptote. This is the graph. Right? The legend for this is x is equal to the amount at time t equal to 0, meaning the amount of the radioactive material, substance, at time t equal to 0. That's x. And the value y is the amount after t years. After how many years? So actually we are given the amount as a function of time. So actually, we could compute how many years will uranium maybe will disintegrate. It's a very long time, right? So it's really very dangerous. The definition of half-life is this. Half-life, the time required for a half sample to disintegrate. Meaning, if we are given this amount and we cut this in half, okay? So what remains will be one half, right? Okay? So the half-life of this is referred to as half-life. If we take one half of the original amount, okay, there is a half-life for that one. It depends on what radioactive substance will be. Okay, to visualize this one, I will try to give you an example. So for this morning, let's just accept these equations here. It was not proven under algebra, but I will be telling you these equations were derived from differential equation in advanced mathematics. I have done this already, but since I am teaching algebra for this morning, I will not give you the derivation of this, but I could derive it. Okay, let's proceed with the example problem. The radioactive isotope sodium-24. So we are given a radioactive substance, and that substance is sodium-24, is used as a tracer to measure the rate of flow in an artery or vein. So they use it in the laboratory, okay, to measure the rate of flow. The half-life of sodium-24 is 14.9 years. Half-life. Meaning to say, if you got 10 grams, you take divided by 2, the half-life of 10 grams will be 14.9 hours. As an illustration for a half-life. Okay? Suppose that a hospital buys a 65-gram sample of sodium-24. So a certain hospital buy the total original amount of the sodium-24 is 65 grams. And it was determined that sodium-24, the half-life is 14.9 hours. This could be taken from data sheet maybe, because they have experimented on this one already maybe. So the half-life of sodium-24 is 14.9 hours, and a certain hospital buy a 65 gram of sodium-24. Okay, the question is this. How much of the sample remain after 24 hours? If originally the hospital bought 65 grams, okay, after how many hours, how many grams will it remain? Because whether we like it or not, okay, that sodium-24 will disintegrate. It's not so long, it's just compared to the so-called uranium, right? But sodium-24, the half-life is just 14.9 hours. So, meaning to say, before it will totally disintegrate, it will not take so long, right? The second question, how long will it be until 1 gram remains? Okay. When the amount of sodium-24 will be 1 gram, how many hours will elapse? Okay. So the second question is, when X is equal to 1 gram, the amount of the sodium-24, what will be time equal to? The first question is, after 24 hours, how much is the amount for the sodium-24? Because whether we like it or not, it will disintegrate. Okay, let's try to bring out the solution. To bring out the solution of this, we must have to use these equations here. We will just accept these equations as a correct one because it was derived from differential equations. Like what I told you, when we reach differential equation, I will derive these equations here. Okay? It was not derived from algebra. Since we are on the so-called application, the algebra book just gave this equation here without giving any proof. But it was derived from the differential equation. So from the general equation y equal to x e raised to xt, there is an x, and there is a y, and there is a t. X is actually the initial amount at time t equal to 0 initially. Y is actually the amount of the radioactive substance at any moment in time. So just specify the time, we could compute how much will remain. Okay, so we are given this exponential equation, exponential, right? That's why the topic for tonight is applications of exponential equations. And for the value k, okay, it was given. That is a natural logarithm of 1/2 over half-life. So if we try to compute for k, we need to solve the particular solution of this one. We must have to compute y as a function of time, right? So to compute for y as a function of time, we need the value of k. And the value of k will be the natural logarithm of 1/2. Half-life of the given problem, solution 24 is 14.9. This is 14.9, 14.9. So if you try to compute for this one, the natural logarithm of 1/2, natural logarithm of 1/2 is actually a negative value. It's less than 1. Okay? We could compute for it. One half is 0.5. We will take the natural log. Hold on. 0.5. Natural log. The natural log of 1/2 or 0.5 is negative 0.693. Then we will divide that by 14.9, divided by 14.9. So the value approximately up to how many digits? 5 digits? Negative 0.04652. It should be negative, because the natural logarithm of any number less than 1 is negative, so this should be negative. Okay? What's the significance of this k here? The significance of this k is if we try to go back to the given equation given by the book, it was x e raised to kt, right? And we now have solved the value of k, negative 0.04652 times time. Okay? So we are now given y as a function of time. Okay? And the first requirement of the problem is, okay, the initial condition at time t equal to 0, initially what the boat is 65 grams. The problem is asking after 24 hours, how much will remain from that 65 grams. And since we are given the relation, it's an easy solution. It's just a direct substitution. So y now will be equal to x. X initially was 65. E raised to k. K is negative 0.04652. The time requirement is 24. The problem is asking for the number of grams that remains after 24 hours. So this should be times 24. If we try to multiply this one, that's why this is actually an exponential equation, right? That's an exponential equation. So if we try to multiply the negative 0.4652 times 24, this is negative 1.16478. And to compute for the value of this one, you should know your calculator, right? 0.04652 times 24, that is negative 1.16478, right? This negative, so you place the negative sign over here. E to the x is on the second function, e to the x, 0.32743 times 65. Okay, the number of grams after 24 hours is 21.2 grams. Okay, this is the amount of sodium 24 that remains after 24 hours from the original 65 grams. Because whether we like it or not, it will decay, right? What's the next requirement? When y is equal to 1 gram, okay, how much time will elapse? Meaning to say, when the number of grams that remains is just 1 gram, how many hours have passed by? And since we are given still the relation, y equal to x e raised to negative 0.04652 t, right? We are given y, right? We are given x, so the only unknown is actually time. So from this equation here, we use this equation. Y is equal to 1, and this should be equal to x, which is 65, times e raised to negative 0.04652 times time. So after the substitution, okay, the only unknown is time. And by using our knowledge of the laws of exponents, right, we could simplify this one. The unknown is actually on the exponent, so to bring it down, we will take the natural logarithm of both sides. Okay, so if we try to take the natural logarithm of both sides, the unknown is on the exponent. To bring it down, we must have to take the natural logarithm of both sides. And if we try to expand the left hand side, the exponent will come down times natural logarithm of e, okay, and this should be equal to the natural logarithm of 1 over 65 is less than 1, natural logarithm of 0.01538. And if we try to compute for t, and so you place the value natural logarithm of e to be equal to 1. Natural logarithm of e is equal to 1. So this is 1. So time now will be the natural logarithm of this over negative 0.04652. And for the natural logarithm of this is less than 1, so it's negative 0.01538, right? We will take the natural logarithm, so it should be a negative value. Any number, okay, less than 1, if you take the natural logarithm, it should be a negative value. This is negative 4.17438 all over negative 0.04652. A negative over a negative is a positive because there is no such thing as negative time, right? And if we try to compute for this one, divided by 0.04652 equals, okay, it is 89.73 hours. If you try to divide 89.73 hours, 1 day is 24 hours divided by 24, okay, so this will become 3 days plus 0.73 hours is minus 3 equals times 24 equals and 17.73 hours. 17.73 hours. Okay, so this is the total time that will elapse when the amount of sodium 24 that remains is only 1 gram. Okay, 3 days and 17.73 hours. Because if you bought this sodium 24 by a, what they call this, expensive amount, actually you should use it immediately. Okay, so you could use the relevance of that one. And it will not pass by 3 days and 17.73 hours because after 4 days maybe it's gone. Right? But the problem is only asking after 1 gram will remain, the total time that will elapse is just 3 days and 17.73 hours. Okay, that's it, guys. That's the application problem of the so-called exponential equations. And one example is actually in the so-called decay of a radioactive substance. This is a real type problem, right? Like that uranium, because uranium is very dangerous. The half-life of that is many thousands of years. Maybe we are out already in this world, but the half-life is still existing. Okay, so for those of you who are studying college algebra, this is for you guys. If you want to subscribe to my channel is at youtube.com/at ProfDavidJDelosReyes. If you want to share it, please click share. Okay? Good morning from Los Angeles. David J. De Los Reyes, Professor David J. De Los Reyes.